Assalamualaikum. Selamat sejahtera. Good morning, everyone.
Morning, Doctor.
Waalaikumsalam. Morning, Doctor.
Okay, thank you. So, welcome to this our class again. SSCM 1993, section 30. Not many students have already joined. I think around 14 students have already joined. So maybe others will join later. Okay, let me first share computer screen. All right, yesterday I've already discussed applications of double integrals in finding mass, moment, and also moment of inertia. If you have any questions regarding yesterday's lecture, before I continue with a new topic on triple integrals. No? I've also uploaded the yesterday's lecture materials into the e-learning. Okay, if there's no question, let's me continue with this new topic on triple integrals. So I introduce you the concept of double integrals through finding a mass of a lamina. A lamina can be viewed as a thin sheet of material covering a planar region here. So now let's move on from finding a mass of a lamina to a mass of a solid. Yeah. Dalam bahasa Melayu solid ni bongkah kan, bongkah. Bongkah yang padat lah, bukan. It's not something hollow. It's not a three-dimensional object that is hollow. It is a solid. Yeah. So for a 3D object, the density is equal to mass over volume. Yeah. For a lamina, density is mass over area. So if rho denotes density and m denotes mass and v denotes volume, then this relation can be written mathematically as rho equal to m over v, which implies m equal to rho times v. So this formula is for the case where density is distributed uniformly or homogeneously throughout the solid. Yeah. So if rho is a constant, volume of the object is known, then mass is simply rho times v. So this is in application. This applies to material like oil, ice cube, steel beam, where they have a uniform density distributed throughout a solid. So what if a density is not distributed uniformly throughout the solid? If it is not constant throughout the solid. For example, in this case of a frozen orange juice, if we buy an orange juice and then we put it in a freezer, it will get frozen, isn't it? But then along the process, there's a settling. There will be settling. And then you see some orange particles here would drop to the bottom. So the bottom part would appear heavier than the top part. So the bottom part is more dense. It's denser than the top part. So in this case, the density is not distributed uniformly throughout the solid. Yeah. So here density varies from point to point. So how do you calculate, say, the mass of such a solid with varying density? So let an object with varying density be denoted as rho equal to rho x, y, z. Yeah, so that means the density varies from point to point in the solid. Yeah. So suppose we have this object here, three-dimensional object, call it G, capital G. So, and suppose the density, this object has varying density rho equal to rho x, y, z, where rho varies from point to point in the solid G here. So what is the mass of this object G with rho, with density rho equal to rho x, y, z? So just as in the case with lamina, we partition in the solid G into subsolids, and let it be, say, rectangular, rectangular solids here. So suppose this is one of them. Suppose we had, like a potato, right? Sometimes we cut them into pieces, into small rectangular pieces, isn't it? So so we assume that a solid G is partitioned into sub cubes here, sub solids here, rectangular solids here, and then suppose this is one of the cube, rectangular cube G, and denote it as G sub K, right? So G sub K has many points. Let's choose one as a representative point, as with coordinate xk, yk, zk here. And this rectangular solid GK, suppose it has dimensions delta x, delta y, and delta z. All right. So what is here, so then the density at the point x, because the density function is known, rho x, y, z. So density at the representative point is equal to rho xk, yk, zk. So what is the mass of the solid, this rectangular solid G sub k? This approximately, mass is what? Density times volume, right? In this case. But the mass is approximately the mass at the representative point. I mean, the density is approximately the density at the representative point. So mass of a solid, the rectangular solid G sub k is approximately density at the point xk, yk, zk, mass times density times volume. And the volume of the rectangular solid G sub k is the product of the dimensions, delta x, delta y, delta z. So what is the mass of the whole solid G? So it is a sum, okay, of all the subsolids that we have partitioned. Okay, if you have partitioned the solid G into n sub rectangular solids, then the mass of the whole object G is approximately the sum of the uh, sum of the what of the mass of the rectangular solids. Suppose if I partition it into n sub-rectangular solids, so the summation is from 1 to n. So this is just an approximation. And then what is the actual mass of this? To get better and better approximation, we use we cut the solid G into smaller and smaller pieces, right? But that would means increasing the number of subsolids. So we define the mass of solid G as the limit of this summation as n tends to infinity. Yeah, and if this limit exists, it is denoted as a triple integral shown below here. We have the triple integral of rho xyz times this volume element dv here, where G is the solid. Okay, where G here is the solid. So the domain G is three-dimensional. Yeah, the domain of G is three-dimensional. Yeah. Okay. So limit is very important. In mathematics, we use limit to define derivative, and we use limit also to define integrals. Yeah. So the concept of limit is very, very important in mathematics. Yeah. Uh, and if, however, rho is constant, yeah, if rho is constant, say equal to 1, then this triple integral then represents the volume of a solid G. Okay, then it is equal. Then this triple integral is equal to the triple integral of 1 dv, and so this is equal to the volume of a solid G. Okay. Any question for this? So here I've introduced you the concept of triple integral from the problem of finding mass of a solid, yeah, with varying density. Okay, may also arise in electricity, as shown here in the side in the right panel here. So in electricity, Q represents charge, right? So suppose Q is the amount of charge in an object, in a 3D object, and V is the volume of the 3D object. Yeah. Then rho, the charge density of object, is Q over V. Is it the total amount of charge Q over the volume of the object with charge? Yeah, the volume of the charge object. Then Q is equal to rho times V. Okay, so the amount of charge of in an object is equal to the density of charge of the object times the volume. So this is for the case if the object is with a constant charge density, then we use this formula. It may happen that an object has a varying charge density. Then the total charge is equal to, then using the same reasoning as in the left panel, then the total charge is equal to the triple integral of the charge density over the region G here. So G here is a solid, yeah, a solid of the is the domain of the object, yeah, in 3D. Any question? Yes. Mm. Any question?
So far so good, Doctor.
Okay, thank you. Thank you. Okay. Now, how do we evaluate a triple integrals? Yeah. The question next is how to evaluate triple integrals over a solid G. Okay, first we look at the case where the G is a rectangular solid. Yeah, this is one example shown here. Yeah, rectangular solid. Yeah, it's all the bounds for x, y, z. They are numbers. Yeah. So if you have a domain G with x, y, z, with bounds for x, y, z are numbers, then that is a rectangular solid. Okay, so this is an illustration of a rectangular solid G. So G has many points x, y, z, but all the points x, y, z are bounded by numbers, some numbers here. So x, which is z, is bounded between z1 and z2. Okay, and x is bounded between x1 and x2, and y1, the coordinate is bounded between y1 and y2. Okay, you can think of this red region on the xy plane like a shadow. You know, it is the you can sometimes previously we denote it as r, right? As r. Yeah. You can think of it as like the shadow of the object G on the xy plane. If we shine a light, from above the object G, then there will be a shadow, right, underneath on the xy plane. So R consists of all points xy bounded between x1 and x2, y1, y2. So then if G is a rectangular solid, then one way of computing this triple integral is using the order dx, dy, dz. Yeah? The innermost integral has limits with respect to x. The middle integral has limits with respect to y. And the outer integral, okay, the outermost integral has limits with respect to z. Yeah, so this is one way of computing triple integral where G is a rectangular solid here. So that means we first integrate with respect to x, okay, and then we integrate the result with respect to y, and then finally integrate the result with respect to z. Yeah, that is one order. But there are other possible orders also, right? We can also integrate using the order dx, dz, dy, dy dx dz, or dy dz dx, dz dx dy, dz dy dx. There are other orders as well. There are altogether how many? 6, isn't it? Using permutations. Yeah, we have x, y, z. If we permute, how many ways to arrange x, y, z? 3 times 2 times 1, which is 6. Yeah, 6 possible ways of arranging x, y, z without repetition. Yeah. So there are 6 possible ways altogether to compute a triple integral with where G is a rectangular object. Yeah, it's a rectangular object. Okay, let's see. Let's do one example. First, we have a solid G represented of consists of all points x, y, z, where mm, x between 0 and 1, say 1 between 0, 1 and 2, and say z between 0 and 2. Okay, and suppose it has a density function rho xyz equal to 1 plus xyz that varies according to the formula 1 plus xyz. So find the mass of this object. Yeah, find the mass of the solid. Okay. So so the formula is the triple integral over a solid G, a region G, rho xy times dv, where rho is 1 plus x y z dv. Okay. So we can choose any. There are 5 possible orders of dv. So suppose I choose dx, dy, dz. Okay. So the innermost integral has limits for x, and x is between 0 and 1. The middle integral has limits for y, and the limits for y are 1 and 2. And the outermost integral has limits with respect to z, and z is between 0 and 2. Yeah. So first we evaluate this integral with respect to x, right? The innermost integral is with respect to x. So what is that? What is the integral of 1 plus xyz with respect to x?
X plus x square yz over
X
2.
plus
X square yz over 2.
yz x squared over 2, right? Because we are treating yz as constant here. We integrate only with respect to x. Yeah. So here x has limits 0 and 1. Okay, so we substitute x equal to 1, we get what? We get 1 plus yz over 2, isn't it? Yz over 2. And when x is 0, it is 0. So now it reduces to a double integral. Reduces to a double integral. So next we integrate with respect to y. What is it? What is the integral of 1 plus yz over 2 with respect to y?
Y plus y squared z over 4.
Y plus y squared z over 4. Yeah, that is correct. And y has limits 1 and 2. Okay. So first we substitute y equal to 2. Then we get what? 2 when y equal to 2. Then we have y squared over 4 is equal to 4 over 4, which is 1. So we have 2 plus z here. Next, we substitute y equal to 1. So we get 1 plus z over 4, right? z over 4, dz. Now it reduces to a single integral here. So before integrating, we simplify the integrand. 2 minus 1 is 1. We have z minus z over 4, which is 3z over 4. And I'm sure everyone, could solve this integral and show that the result is 7 over 2. Since we are dealing with solid mass, so it is what? Unit, it is kilogram, right? Kilogram. Something to do with kilogram or mass, unit mass, yeah. So 1 over 2 unit mass. Okay, so this is one way of evaluating this triple integral using the order dx, dy, dz. There are 5 other ways, yeah? 5 other ways to evaluate this integral, and they should all come out the same value. Right? They should give the same value. So I leave it to you, to try using other order besides dx, dy, dz. Yeah. Any questions so far for this example? So write down clearly, the solution. Write down dx, dy, dz. Sometimes student, they are not particular about writing dx, dy, dz. Okay, suppose we want to evaluate. Sometimes we want to evaluate triple integrals with no reference to applications, with no reference to solid. Okay, suppose we want to evaluate this triple integral yz cosine xy dv. Okay, where the g is equal to, G here is a rectangular solid also because all x, y, z are bounded by numbers. X is between -2 and 1, and y is bounded between 0 pi, and z is bounded by 1 and 4. Okay, so G is a rectangular solid here because all the numbers all the variables x, y, z here are bounded by numbers. Yeah. Okay, so as explained before, then we have 6 ways of evaluating this triple integral. But sometimes one order is simpler than the others. What do you think? Okay, what is that? What is that thing? Delete. What is that thing? Where does it come from? Okay. Which one is if we integrate with respect to y first, then we have to use integration by parts, right? If I choose say dy, dx, dz, then we have to use integration by parts, isn't it? So that means it's not suitable to use this arrangement. Integrate by parts. So it's not suitable to use this arrangement. It is possible, yeah, but takes a lot of work because it involves integration by parts. What about the arrangement cosine xy, say dx, dy, dz? So we integrate with respect to x first. Okay, so, but x is inside cosine. And then we need to integrate with respect to y. Again, that would involve integration by parts. Yeah. Requires integration by parts. Again, when we want to integrate with respect to y. Yeah. So this is also not a good choice. What about can we integrate with respect to z first? Yeah, because z is outside cosine, right? Z is outside cosine. So so z, let's integrate with respect to z first because z is outside cosine. And let's if we put dy dz, also not good. Dy dx is also not good because then again it requires integrating by parts, isn't it? Integrating by parts. So let's try then yz cosine xy dz dx dy. Okay, let's try this. Dz dx dy, because the z is outside and x is in cosine, inside cosine, and y, you have y outside and inside. So okay, let's try this one. So using this
Or
arrangement,
input A is less
is that? What is the integral of y cosine xy with respect to x?
Y squared sine xy.
With respect to x. With respect to x.
Oh yeah. Y.
Think of y as a constant here.
Sine
If we
xy
integrate, yeah.
x.
If I integrate cosine alpha x dx, what is that? Sine alpha x over
Sine
alpha,
alpha
right?
x.
Hmm.
Oh yeah.
Okay, so now alpha is y. So the result
Sine
is
sine xy. Sine xy.
yeah, sine xy. Or maybe we can write it first as y times sine xy over y, isn't it? X between -1 and 2. So y cancel out, right? So the integral of y cosine xy with respect to dx is the same as sine xy actually. Yeah. So what do you know? So 0 to pi. First we substitute x equal to 2, so we get sine 2y minus what? Then we substitute x equal to -1, so sine. Okay, let's not use too many brackets. Sine 2y minus sine of minus y, isn't it? Yeah, and x is equal to -1, then xy becomes -1. But yeah,
May I interrupt? The limits of x, is it you flip already? Why is it flip?
for x tipped really?
Yeah, from the line
X is between
is
-2 and
one.
1, that's correct. Y is between 0 and pi, that is correct. Z between 1 and 4, okay, that's correct.
1 and -2, but you suddenly change to 2 to -1.
Oh yeah, oh you mean at this stage? My mistake, my mistake. Should be here -2, 1. Thank
Yeah.
you.
Yeah.
Thank you. Should be -2 here and 1. So I need sine y here, right? Sine y there. Minus sine -2y. Yeah. Okay, thank you. And sine -2y is the same as minus sine 2y, isn't it? Because we have this property that sine is an odd function, right? Sine is an odd function. So we have minus and minus, so it is plus now. Sine y plus sine 2y. And I'm sure you can evaluate this integral by yourself. So let me show you. The result is 15, equal to 15. Okay, equal to 15. So I want you to try that out yourself to evaluate the last integral, which is a single integral. So show that it is equal to 15. Yeah. So sometimes we just want to evaluate double integrals with no reference to a solid, a mass, or any other application, yeah, just for the sake of evaluation of triple integral here. Any question for the second example here? So what do you know? With this order, dz dx dy, no integration by parts is necessary. Yeah, there's no integration by parts involved at all here. Unlike if you use the order dy dx dz, then you need to use integration by parts. Yeah, so sometimes using one order is easier than other certain orders. Yeah, yeah. So it's good to think before evaluating triple integrals. Yeah. Don't just simply use dx dy dz. Every time triple integral, you want to use dx dy dz. So sometimes that is not the best. Sometimes that's not the easiest way. Okay, so that's for evaluating examples of integrals with G is a rectangular solid, yeah, rectangular solid. Okay, let's consider a more challenging G, solid G, where it is bounded between two surfaces. Okay, so in this diagram, this is an illustration where we have a solid G bounded above by the surface z equal to f1 xy, and the lower surface is represented by z equal to f2 xy. Okay, we have already discussed graphs and regions, domains, right? And you know that the graph of a function of two variables is a surface. Yeah. So what if we have a solid G or an object G bounded by two surfaces as shown here? Yeah. Then Z is between. Okay. Now Z is no longer bounded by numbers, and Z is now bounded by two functions of two variables here, f1 and f2. Yeah. And if this is the case, then we must integrate with respect to z first. Okay, for this triple integral, we must integrate with respect to z. The innermost integral must be with respect to z, because z is bounded, has limits, upper and lower limits as functions of x and y. Okay, yeah, and then so first we integrate with respect to z, and then we integrate over r. R is this it's like a domain xy. Okay, is a x. Imagine if I shine this solid G with a light from above, then there's a shadow underneath, right? Yeah. So this shadow on the xy plane consists of all the points xy of the object G. Yeah. So the point xy is in a region, some region R here. Okay. So we first integrate with respect to z, and then we integrate the double integral over a region R here. And if in addition R has this limits, x is bounded by numbers and y is bounded by two functions of x, then we must integrate with respect to y first. After integrating with respect to z, Then we integrate with respect to y, and finally with respect to x, because x is bounded by numbers. Yeah. So we must use this order. If r is given as shown here. And if f is equal to 1, yeah, so we know that if f is equal to 1, this triple integral calculates the volume of G. So if z is bounded by the surfaces f2 and f1, then the integral of 1 with respect to z, and then we substitute z with the upper and lower limits and takes the difference. So this is the result. So if you want to find the volume of a surface of a solid G bounded by two surfaces f1, f2, it is equal to the double integral of the differences of the functions of f1 xy and f2 xy. Okay. So let's see some examples of evaluation of triple integrals involving a solid G bounded by surfaces. Okay, this is a sample a final exam question. Using triple integral, determine the volume of a solid in the first octant bounded by the plane y plus z equal to 2. The plane coordinates and the parabolic cylinder represented by x equal to 4 minus y squared. Okay, this is the question. Using triple integral, determine the volume of a solid in the first octant bounded by the plane y plus z equal to 2. The plane coordinates and the parabolic cylinder x equal to 4 minus y squared. Okay, we know that the volume can be calculated by this triple integral, right? Yeah. But what is G here? What is a solid G? G consists of all points x, y, z. Yeah. G consists of all points x, y, z. What is G? It consists of all points x, y, z, such that what? What are the bounds for x, y, z? This is what we need to determine. So look at the question again. What is the information given? The solid in the first octant. Okay. The solid lies in the first octant. What does it mean? First octant.
For
What does it mean?
XYZ is positive.
Yeah. Remember
Greater than
yes. Remember 3D. Okay, the XYZ plane, the XY, this XYZ axis divide space, a 3D space into 8 parts, right? Into 8 parts. That's why it's just called octant. So the part where x greater than 0, y greater than 0 is, okay, the region where all x, y, z greater than 0 is in the first octant. It is in the first octant. Okay. What else? Bounded by the plane y plus z equal to 2. Bounded by the plane y plus z equal to 2. Z, this implies what? What is this line on the YZ plane? It is a line, right? It is a line. Intersects the y and the intercepts are 2 here. This is a line, so it is a plane. It is independent of x, so it is a plane. It's a plane like this that contains the line y plus z equal to 2. And parallel to the x-axis. The plane is parallel to the x-axis and containing the line y plus z equal to 2. What are the plane coordinates? Plane coordinates means what? All the xy plane, the z plane, and the yz plane, right? These are called the plane coordinates. The xy plane, the yz plane, and the xz plane. And we have a cylinder as well. It is called parabolic cylinder. It's called a parabolic cylinder. X equal to 4 minus y squared. X equal to 4 minus y squared. So on the xy plane, it is a parabola. X equal to 4 minus y squared. When y is 0, x equal to 4. When x is 0, y equal to plus or minus 2, right? Plus or minus 2. So we have something that looks like this, something that looks like this. So it is a parabolic cylinder. It means you have things that looks like this, things that looks like this. Okay, so some things that looks like this, and then okay, So this parabolic cylinder, we slice it with using a plane. Can you imagine how this 3D object looks like? One of the challenging of this question is to be able uh, to sketch the graph of the object G. That's one of the challenges here. So can you imagine what is it? Is it not that looks like something like this? Right? Is it not something that looks like this? Yeah. Am I right? Parabolic cylinder. We slice it by a plane, and then in the first octant only. Okay, so this is actually what the object G looks like.
Yes, okay.
Yes?
Yeah.
Yeah. Okay, so now we
Doctor,
determine the bounds.
this diagram got any marks here?
Of
So complicated,
sure.
this one.
Of course. Otherwise, how one can determine the bounds for G if you don't have the correct sketch of G? So now it is clear, isn't it, from this diagram that Z is bounded by the xy plane, so greater than 0, and below by the plane. Here, this implies a Z equal to 2 minus y. So Z is bounded by the xy plane and bounded above by the surface. Z equal to 2 minus y. Yeah. Okay, so all point Z is between the xy plane and below the surface, which below the plane, Z equal to 2 minus y. And what about x and y? X and y is in this region here. Yeah, it is in this region R, in the first octant. Okay, all points x and y are in this region R here. So what are the bounds for R? This equation is what? Y x equal to 4 minus y squared. This is x equal to 4 minus y squared. So it is clear that x is between a function. X is greater than 0 and less than 4 minus y squared, right? Yeah. And now y must be bounded by numbers. Y is between 0 and 2. Okay? Y is between 0 and 2. See, so with the help of the sketch of the region G, we can determine the bounds for x, y, z. Otherwise, without the sketch, how one would be able to determine the bounds? Yeah. Yeah. So if in the test or in the final, sometimes students solve this problem without giving a sketch, and yet he managed to get X, Y, Z correctly. So that's fishy to me. How in the world the student managed to get this X, Y, Z without even a sketch? So that's suspicious, Did he get it from somebody else? I don't know. Yeah. So now we have found the bounds, okay, for G here. Consists of all points x, y, z. So G consists of all points x, y, z, such that, yeah, these conditions here. So now we are in the position now to calculate the volume V. What order should we use here? What is the correct order?
X and Z have to be inside, and then Y have to be outside.
Yeah.
Yeah.
It
Yeah,
should
so
be dz first, right?
X
It should be
yeah.
dz first. Because z is bounded by surfaces 0 and 2 minus 1. Okay, what next? Is it
X
dx dy or dy dx?
dx dy.
Dx dy, because x is bounded by a function, isn't it? It's a function of y. So x is bounded between 0 and 4 minus y squared. And finally, dy. Okay, the one that's bounded by numbers it should be the outermost integral. Okay, so this is the correct setup for calculating the volume of this object G. So first we integrate with respect to z. The result is z. Okay, z is between 0 up to 2 minus y. And then we substitute z with the upper limit. It is 2 minus y. Substitute z equal to 0, it's 0. Okay? Is this correct? Yeah. Yeah. So it is equal to 0 up to 2 times the integral of the inner integral followed by the integral 0 up to 4 minus y squared. We have this integral 2 minus y dx dy. Okay? So now we integrate this with respect to y. What is it? With respect to x. What is the integral of 2 minus y with respect to x?
2x minus xy.
Or more simply, 2 minus yx, isn't it? Because 2 minus y is just a constant, right? It is also the same as what you have said just now, 2x minus yx, yeah. And then x is between 0 up to 4 minus y squared. So next we substitute. First substitute what? X by 4 minus y squared. And when x0 is 0, so we are left with this single integral here. Okay. So I'm sure all of you can evaluate this integral. So I'll leave it to you to show that the end result is 20 over 3. Since we are dealing with volume, we put in a unit cube here. Okay. Any question? So the most challenging part is the construction of the object G, right? And
Yeah,
also to
drawing.
determine the bounds x, y, z. Yeah, it's a challenging part here. If you fail to get the sketch correctly and the bounds correctly, then you will get a wrong answer. Yeah. But of course, marks will also be given for the methods, you know. For methods, you will get mark for methods. Yeah. So, well, any question for this example? Okay, let's try another example. Okay, this time related to finding a total charge. Yeah? Yeah, an object occupies the solid region bounded above by the sphere x squared plus y squared plus z squared equal to 9, and below, bounded below by the xy plane. If the charge density, okay, if the charge density of the object at any point is equal to its distance from the xy plane, find the total charge on the object. Okay, this is a problem from a calculus book. It's an exercise problem, so I have to work out the solution. It's not given as an example from a calculus book. This is from an exercise problem from a calculus book, so I have to work out the solution here. So in preparing the course lecture, I have to look at several calculus books. I have 5, 6 calculus books in my office here, so I have to look at choose several pick out several suitable examples. Yeah. Okay. Again, right? We know that charge is equal to what? The total charge is Q. As we had discussed before, the total charge is represented by a triple integral over a solid G. This is rho, right? Rho x, y, z dv. Yeah. So, what is rho and what is G here? First, let's sketch this object G. Yeah? In order to determine the the bounds x, y, z correctly. Okay, mentioned here by the sphere, bounded above by the sphere, and bounded above by the sphere and below by the xy plane. So this must be a sphere above the xy plane, right? This must be a sphere above the xy plane. Um, it is a sphere centered at the origin, the top hemisphere. It is a top hemisphere. What is the radius? What is the
3.
radius? 3, yeah, 3.
Square root of 9 is 3.
9 is 3, yeah. It is a top hemisphere. What is the charge density? So we know that Z is bounded by. So we know that Z is bounded below by the xy plane, which is 0. Z equal to 0. And what is the top hemisphere? It is x squared plus y squared plus z squared equal to 9. So that means z squared equal to 9 minus x squared minus y squared. So we want the top hemisphere must be positive, right? A positive square root. The bottom hemisphere is z equal to minus the square root. Yeah. So z is bounded above by this top hemisphere here. So now we know what is the what the bound for z. What about xy? Xy is in this region, right? Xy here. This blue region. Yeah. So the point xy belongs to the blue region here. So what is the bound for x and y? It is circular. Remember? If the region is circular, what is the suitable coordinates? What is the suitable coordinate if it is circular?
Equation of ellipse, right?
What is the coordinate system that we should use if it is circular?
X squared plus y squared.
Rate polar coordinate.
Polar coordinate, yes.
Oh, okay.
Okay, right? If it is circular, it is advisable to use polar coordinate or r theta. R theta, right? Yeah. So therefore r is between what and what? What is the radius again here? 3, isn't it? 3. So r is between
0 to
and
3.
3, and theta, since this is a full circle, theta between 0 to
2 pi.
2 pi. Okay. So now we have enough information here to evaluate this triple integral. Oh no, not yet. There's one thing. The charge density. The charge density is equal to its distance from the xy plane. The charge density, so if I have a point here, x, y, z, the charge density is equal to its distance from the xy plane. What is the distance of a point x, y, z from the xy plane?
3.
No, x, y, z can be any point. Not on the surface only, but it can be any point inside. X, y, z can be on the surface as well as inside, So what is the distance is equal to z, isn't it? It's equal to z, the height of the point from the xy plane is equal to z, right? And z is positive because this object is above the xy plane. So rho here is equal to z. So we have z here and dz. For the area element, let's use a dA first. So z is between 0. This is over r. The double integral outside is over the region r. And the innermost integral z is between 0 up to 9 minus x squared minus y squared. Yeah. And the integral of z, so first we integrate with respect to z. The integral of z with respect to z is z squared over 2, right? And z is from 0 up to the square root of 9 minus x squared minus y squared. Yeah. So when we substitute z squared, is the square root disappears, right? When we square z, the square root sign vanished. Yeah, so we have 9 minus x squared minus y squared. Yeah. Don't forget 1/2 as well. Let's put 1/2 outside because it is a constant. So it's reduced. So now the triple integral reduces to this double integral over this region R. So now we want to apply the polar coordinates, okay? Because R here is circular, we want to apply the polar coordinates with this bound for R and theta. And what is x squared? X is R cos theta. Remember the relationship between the Cartesian coordinate and the polar coordinate. So x squared plus y squared is r squared, isn't it? So here we have 9 minus r squared. Okay. Yeah. And r, we can choose, because r and theta are numbers, we can choose. Remember, we also have r, dr d theta. For the area element in polar coordinate, it is r dr d theta. So don't forget that r. Sometimes students forget that r. When doing the conversion from the Cartesian coordinate to the polar coordinates. Yeah. So in this order, the inner integral is with respect to r. So r is between 0 up to 3. And the outer integral is with respect to theta. And theta is between 0 up to pi. So this the integrand, if I multiply r into the bracket, it is 9r minus r cubed. Yeah. Minus r cubed. So first we integrate with respect to r. What is that? Integrate with respect to r. What is the result?
Nine r squared over 2 minus r to the power of 4 over 4.
Yes. Okay. So r from 0 to 3, yeah? So when r equal to 3, so we have 9 times 9, which is 81 over 2. And r equal to 3, r to the power of 4 is also 81. And r is 0, it's 0. Okay, so what is that? 81 times 3/4, isn't it? This 81 times 1/4, right? 81 times 1/4. Yeah. So we have 81 over 4, right? Yeah. So it's just a constant. It's just a constant. So integrate that with respect to theta. This 81 4 times theta. Theta is between 0 up to 2 pi. So we have 1/2 81 over 4 times 2 pi. Okay. So 2 cancel out. So we have 81 pi over 4. That's the total charge. Total charge. What is the unit for charge? In electricity, what is the unit for charge? Ohm, huh? Ohms.
Coulomb. Okay.
Ohms, right? Charge.
Ohms is for
Charge.
ohms is
Huh?
for
what?
resistance. Ohms is for resistance.
Resistance. Okay.
Yeah.
What is the unit for
Coulomb
charge?
is Coulomb.
Coulomb. Coul.
I don't know how to spell.
I should know.
This one
Electrical
this one
student.
seldom used. Yeah, this one seldom used.
Coulomb, right? Coulombs, isn't it? The unit for charge. Correct me if I'm wrong. It is Coulomb, right? Coulomb. So that's an example of evaluation of triple integral for finding a charge of this object G here. This is the object G. Ada soalan untuk contoh ni siapa-siapa? Why are you so quiet, man? Why are you so quiet, huh?
So far so good.
Yeah. Yeah, sometimes during class, students seems quiet, so as if they understand everything. Yeah.
Yeah,
But when
I
it
haven't
comes to
tried
the
even
test, when it comes to the test, final, then we realize there's so many things they do not fully understand.
Yeah, I haven't tried even know.
Okay, sometimes we want to evaluate triple integral just for the sake of evaluation, nothing to do with applications or anything. For example, suppose okay, let's do one more example and then we stop. Suppose D is a solid bounded by the paraboloid, bounded by the paraboloids z equal to 3 minus x squared minus y squared, and z is between, then z is another paraboloid, second paraboloid, minus 5 plus x squared plus y squared. Okay. With this additional condition again, x greater than 0, y greater than 0. Okay. And question is, evaluate this integral over a solid region D, y dv. Okay. What is the first thing we need to do?
Draw the diagram.
Sketch, yeah, sketch the object D. Yeah, and these are paraboloids, right? They are common surfaces. So we have already discussed sketching paraboloids. We will stop at 12:40 because we did not take a break. Okay, what is the paraboloid? Z equal to 3 minus x squared minus y squared. When there's a paraboloid that opens downward and another paraboloid that opens upward, right? So when y is 0, look at the traces. Look at the traces. So let's first consider z equal to 3 minus x squared minus y squared. So when x is 0, we get z equal to 3 minus y squared. When x is 0, it is on the which plane? The yz plane, right? The yz plane. Yeah, so z equal to 3 minus y squared. When y is 0, it is 3. Okay, it is 3. Yeah. When z is 0, so plus minus square root 3, right? Square root 3. Yeah, so we want this, so this is the paraboloid. We want the case where x greater than 0, right? Here we are also given this condition. So let's just consider the right arm. For x greater than 0, y greater than 0. So we have something that looks like this. And then when y is 0, z equal to 3 minus x squared. So it has the same shape also, right? But on the xy plane, something like this. Okay. Now let's go to the second parabola. It's minus 5 plus x squared plus y squared. So the first parabola opens downward. Opens downward. So again, we look at the traces. X is 0, z equal to minus 5 plus x squared. So when x is 0, z equal to minus 5. And what is it? And then opens upward, right? In this case, we have a parabola that opens upward, square root 5 here. Like this. Okay. When y is 0, z equal to minus 5 plus y squared. Z, no, this, what I've drawn is on the z. Should be on the first one, z equal to minus, it is on the what? And x is 0. Yeah, this is correct, the zy plane here. And the xy plane, when y is 0, on the xz plane, it is also a parabola. Here, this is square root 3, square root 5. So looks something like this. Yeah.
Doctor, the equation z equal negative 5 plus x power 2 should be y power 2.
Which one?
The equation x equal to 0 should be y power 2, not x power 2.
Oh, okay. I'm sorry. Yeah, you're right. The blur lah. Looking at the screen too long here. And y is 0. Yeah, x squared. You're right. But the diagram I've drawn is correct. On the ZY plane, it is correct. Yeah. So the other on the... No, how you can see sometimes it's a challenging. Huh? Challenging. Maybe I should draw minus 5 a little bit at the bottom here. Because minus 5 is something like this. And you have the arm, this arm here. Okay, can you imagine this this object? So there's an intersection somewhere, isn't it? There must be an intersection somewhere. This is the intersection, right? Intersection. There must be an intersection somewhere. So this object is an object between these two parts here. Okay. This that's for x greater than 0, y greater than 0. So this is the object G, bounded by the two paraboloids for x greater than 0, y greater than 0. So what is the R? We know Z is bounded. We know that Z is bounded between the lower paraboloid, which is 3 minus x squared minus y squared, and the upper paraboloid, what is the upper paraboloid? Minus 5 plus x squared plus y squared. Okay, what about xy? What about point xy? We have intersection of paraboloids here, right? So that's what we need to calculate. What is the curve of intersection of the paraboloids? The paraboloids intersect in a curve. What is the curve of intersection of the paraboloids? We equate the two paraboloids. 3 minus x squared minus y squared equal to minus 5 plus x squared plus y squared. So this implies what? We have 2x squared plus 2y squared equal to 5 plus 3 is 8. Yeah, which is a circle, right? X squared plus y squared equal to 4. So it is the curve of intersection is a circle here. It's a circle. This one here. It's a circle. So this is the region R. The point xy in this region R there. Inside a circle in the first quadrant. It's xy. It's a circle here of radius 2. So again, polar coordinate is suitable here. All right. So now we are in position to evaluate the given triple integral. First, we integrate with respect to z, okay, y, dz, and then dA, dA for evaluation over the region R. We're going to use polar coordinate again here. So z in the innermost integral with respect to z has bound 3 minus x minus y squared minus 5 plus x squared plus y squared. Yeah. So integrate with respect to z, we have yz. Z between minus 3 minus x squared minus y squared. The upper limit is minus 5 plus x squared plus y squared dA. Yeah. Let's put dA first. So we have now substitute the values of z. Minus 5 plus x squared plus y squared minus, then we replace z by the lower limit, dA. Okay. All right. We'll continue this later. But for those who are willing to try on your own, show that the result is equal to 128 over 15. Yeah, that is the answer. Okay. We'll discuss the detail of the calculation later on. Yeah. Okay, enough for today. Let me show you the QR code for your attendance. I plan to give you a third assignment. I'll give it to you today, tomorrow. Your next assignment, which will be due next Wednesday, yeah, or Thursday. What time class starts today at, but why 14 April? What is this? I didn't choose it correctly, or I should choose this one. 11 a.m. Okay, so please scan this QR code for the attendance. Okay, you may leave the class after scanning.
Thank you, Doctor.
Thank you.
Thank you, doctor.
Thank you.
Thank you, Doctor.